Okay. So let's get started. Today, guys, once again, chapter 20.2, which is on charging objects. Okay, so define charging an object. If I say I'm charging an object, what does that imply? Okay, so it's gaining or losing electrons. Okay, so today we're going to talk about different methods by which an object can gain or lose electrons. Specifically, there's going to be two. Okay, and so our two methods are going to be conduction and induction. Remember when we were conducting heat? That was conducting heat by doing what? Charge the T? Touch. Okay. So conduction, the same as with conducting heat by touch. Conduction is going to be transferring charge by touch. Okay. And then induction, if I induce something, okay, from a distance I cause it to begin. Okay. And so induction will be not through touch. Okay, but we'll spend more time on that in a second. All right, so anytime an object is becoming charged, we said that we have to add or remove electrons. Okay, but I want to add to that just a little bit. Okay, we don't just add or remove electrons, we only relocate electrons. Okay, so the implied difference there is relocating versus creating. Okay, we can never create charge. Okay, I can't make an object negatively charged by destroying some protons. Okay, and I'm not going to make an object positively charged by destroying some electrons or adding protons. Okay. Okay, so charge is never created or destroyed, only relocated. So by implication, if something becomes negatively charged, I know that something else has to become positively charged. And specifically, if something gains 2 coulombs of negative charge, I know something else had to lose 2 coulombs of negative charge, or it would become 2 coulombs of positive charge. So if it had 8 coulombs, now it has 6, right? Making sense? Okay, so we're going to take a second and go in depth with that first charging method, which is conduction. Okay, so conduction occurs when a charged object touches another charged object. Or it could be a charged object and not charged object. But the idea, guys, I have to have a charged object touching something. And actually, it's going to end up being they could be both neutral, but we'll get there in a second. It's through touch. All right, so in order for this kind of traditional conduction to occur, one object has to be more negative than the other one. What I mean by more negative is the electrons in one of them have to really want to go to the other one. If I put a whole bunch of electrons near each other, what do they typically want to do? They want to separate, right? Okay, so if I have an object that has a whole bunch of electrons, and I touch it to an object that doesn't have a whole bunch of electrons, do y'all agree that those electrons want to move to the other object?
Yes.
Okay, because those electrons want to separate from each other. They're getting the biggest amount of distance between each other. Okay, so charge always flows from the more negative object to the less negative object. Unless there's some sort of outside force. But for right now, we're assuming there's no outside force. So I'm not talking about if I plug up a battery to it. Just kind of naturally occurring is what we're talking about. All right, so let's say I have two objects. One very highly negatively charged, and one not so negatively charged. Okay, and I'm using the negative signs. The more negative signs I'm saying is more negatively charged. Okay, so I'm going to move those together so that they are touching each other. Okay, so I know that the electrons on the left, they want to separate, and so they will separate. Okay, and when they separate, that's going to induce a higher amount of charge in the right-hand block. Okay, so what I've seen there is conduction. Now if I take these and separate them, you see how the right-hand block is more charged now than it was before. But the left-hand block is less charged than it was before. Okay, this typically happens with conductors. So if I take one metal and I put it up to another metal, that's kind of what we're talking about. Okay, however, we can have the conduction or the movement of charge through touch not inside of a conductor as well. And that tends to build up static electricity. Okay? So static electricity, guys, is built up when two surfaces rub together. And most of the time, these two surfaces are not going to be conductors. So you're walking across the carpet and you have on socks and your socks are rubbing across the carpet and that's, then you walk up and zap somebody. Or, isn't there a cartoon about that? Somebody's just like walking around. I think that's on Family Guy at some point. He has socks and he walks around the carpet and then zaps people. Or when we're lazy and we sloth out of our car as opposed to getting out of the car.
I
we
pay
might.
attention to that and I don't.
Huh?
I don't get out of the car I just get out.
Have you tried watching other people get out of the car?
Can you
Maybe a comparative process might be.
Can I just be more electric or have it built up in my body?
No.
Well, something's wrong because I'm not getting out of my car
When you say more electric, I'm thinking no, you weren't born in the 70s.
More electrons, I guess. I don't know.
Okay, so two electrically neutral objects, guys, can be rubbed together to generate charge. If I'm generating charge, I know that one of the objects is going to become positive, the other one's going to become negative. Okay? And that separation of charge is going to be caused by something called the adhesive molecular force.
Adhesive means separation. Adhesive means...
Adhesive is sticky.
What about cohesive?
I don't know. That's chemistry stuff. Don't ask me chemistry stuff.
It's water
That's something. Anything that's adhesive is together. I don't think there's any adhesive that means separating. Huh? But if you say, adhere to your moral principles, that would mean stick to them. Okay, so this adhesive molecular... Can I go?
Wait. There you go.
Okay, so this adhesive molecular force, guys, is what holds atoms together. Specifically, our adhesive molecular force is going to be that attractive force between the electrons and the protons. Okay, so the electrons are zipping around the nucleus, and if there were no force there, then they'd be in a we had a name for that kind of orbit, the increasing orbit, and they go flying off. Okay, so we have this adhesive electric force that holds the electrons in. So obviously the electrons that are closer probably have a stronger adhesive force, and the electrons that are farther out are going to have a little bit lower adhesive force. And that's also true for different elements. Some elements have a very strong adhesive force, and some elements have a lower adhesive force. Okay, so when two different materials are placed together, okay, the adhesive molecular force it tries to hold them together. Think, I have an atom here, I have an atom here. This one has electrons, right? And so so there's going to be some forces. There are going to be some forces between the electrons of this one and the protons of this one. and back and forth. Okay, however, we're a little bit stronger than that adhesive force, so I can pull my hands back apart. That's no problem. However, if one of the substance has a really strong adhesive force and one of the substance has a really weak adhesive force, then when I separate those, some of the electrons from the weak might stay on the one from the strong. Or you see where I'm going here? When they rub past each other, those electrons get ripped off from the weak adhesive force by the strong adhesive force. So I have two neutral objects. They rub past each other. Some electrons from one get ripped off and get deposited onto the other one. Okay, whichever one has the strong adhesive force tends to become negatively charged because it's gaining electrons, and whichever one has the weak adhesive force is going to become positively charged because it's losing electrons. So this method of conduction will happen in insulators as well, because it doesn't require those electrons to be able to flow through the material. It just requires electrons to get ripped off, and not you bought some chicken and it turned out to not be a good chicken way.
What is sparsely filled sugars?
Well, I haven't read this. I don't know. Where does it say that?
What?
I don't know what I meant there. I'm assuming that's what I meant, and to be honest, I don't know if that's true. So just ignore the sparsely filled shells part. Let's just go with ones with the strong adhesive molecular force will gain them. I don't know what I meant there. I think that's a little presumptuous. I probably just said that. I wrote this PowerPoint last year. All right, so we've kind of categorized how elements perform. Some elements strong, some elements weak, and that series is called the triboelectric series. And y'all don't have to memorize these. Okay, so the higher we get on the triboelectric series, guys, those are the ones that tend to lose electrons. So they have the strong or weak. They have the weak adhesive molecular force. Okay, the lower on the triboelectric series will tend to gain electrons. And there's really no rhyme or reason here. The only thing I've noticed is the ones in the upper tend to be like more organics. You'll see like human skin, rabbit fur, glass. Glass is not organic, but whatever. And then at the bottom, I see like more kind of synthetic stuff. So I don't know if that's like a broad rule, but that's just what I've noticed. Okay. What now? Okay. So this tells us the rule for will two things rub together and create charge. If you rub something at the top against something at the bottom, then it creates charge.
If you rub two tops.
So if you rub two things at the top together, whichever one is higher up will lose electrons, and whichever one is lower down will gain electrons. Okay, and it might be very, 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 very minute, but there would be some effect there.
What about the same thing?
Huh?
What about the same thing?
If you did the same thing, I would assume nothing would happen.
You just rub PVC on yourself and you can just like zap the crap out of people?
I don't know how effective that is. Yeah.
Okay.
Well, it's weird.
Get some PVC.
Okay. So,
rub it on your skin.
here guys, I have
I've got some, so it should be interesting.
If you do get beat up, don't tell them I gave you that idea.
Okay, here I have, looks so much better on this projector. I have a rubber balloon. Okay, rubber was low on the triboelectric series and some cloth which is higher on the triboelectric series. And so I'm going to just rub the cloth against the balloon. So the balloon should be getting what kind of charge? Negative or positive? Negative, okay. And this should be getting a positive charge. This is just an electroscope which detects the presence of electric charge. Okay, so what we see is as this gets close, okay, we see that there is indeed charge on the balloon being built up. You hear that little pop? Okay, the little pop is charge dissipating from the balloon. You can't see it, but y'all didn't hear it? I wonder if we can see it. Let's turn the lights off. That's dramatic. Alright, let's see.
Yeah.
You see it? I heard it. I can't see it. I can just hear it.
Like that, you can see it.
Well, yeah. Pop.
Ooh, you should do that.
Well, the balloon gets what kind of charge? Negative. We said the top of this gets negative, and so it actually would have a little bit less effect than typical. Another thing with the triboelectric series, guys, the way this works, okay, down at the bottom, I have something that is very, very high on the triboelectric series, okay, and some rubber rubs against it. Okay, so that rubber gains electrons when it's down here. Okay, the rubber comes up to the top. I have something up here that's lower on the triboelectric series than rubber. Okay, so the rubber deposits the electrons on that, and then that deposits the electrons on here. Make sense? You need a drawing of that? No, I was just telling you. This? No. Yeah. Alright, conduction, we good? And the triboelectric series, good? Okay, so the second way of building up charge is called induction. Okay, in induction, we're inducing charge. Okay, we're not going to be adding or removing charge, we're going to induce charge. Okay, so induction occurs when charges separate without touch. Okay, so what is of note here is with induction, we said, oh dang, I didn't mean to turn that on. I'll turn that on later. No, let me just go ahead and turn it back on. Whatever. So with induction, I'm not adding any charge. Okay, I'm just separating charge. Okay, so the total amount of, if I'm inducing charge in a substance, the total amount of charge after I induce is equal to the amount of charge before I induce. All I've done is separate the charge. Okay, so there are no additional electrons, there's no additional protons. I've just moved the electrons over here and not moved the protons. Okay. All right, so let's look at an example of that. Let's say I have two objects. We'll say one sphere is negatively charged, then I have a rod, and we'll make the rod negatively charged as well. And maybe the rod's not a conductor, so since the rod's not a conductor, we'll say those electrons on the rod won't move. Make sense? Okay, so I'm going to take the rod and I'm going to move it closer to the sphere. Okay, so when I move that rod closer to the sphere, what do the electrons in the sphere want to do? They want to move away, right? So they're going to move in the opposite direction of the rod. Okay. However, the absence of electrons is positive charge, right? So what I end up with is a sphere that's negatively charged on one side and positively charged on the other side. That's induction. Okay, so really it appears as though that sphere has more charge than it did before. because I've built up, the negative charge has amplified on one side and the positive charge has amplified on the other side. But really I just took the charge and separated it. Let's say I took a wire and I attached it on the negative side. What would all those electrons do? They flow down the wire and I end up with a sphere that was positively charged. Okay, so that would be conduction and induction together. All right, so induction is going to play an important role in lightning. And I'm going to skip this first point because I think we've already talked about it. Yeah. Okay, I'm just going to kind of skip the rest of these notes and just kind of walk y'all through it. Because frankly, they're just kind of boring. And there actually is one more good animation in there, but... Huh? Yeah, I'll do the animation later. No. I didn't waste my time making that animation for no reason. Okay. So, can y'all? Right. Okay. Let's get some good colors. I need gray. Gray? Do I have a gray? No? That'll work. Okay, so let's say I have a cloud. That's my best cloud. Yeah. And here's the ground. And so the ground, guys, is typically neutrally charged. Okay, so I mean I might have a few pockets of positive and negative, but we'll just say the ground is going to be neutrally charged. Okay. And so this cloud is drifting along, and maybe it's a thunderstorm. And so if it's a thunderstorm, typically at the bottom region of a thunderstorm we will have negative charge. Okay, so the bottom region is predominantly negative, typically, and the top region is typically predominantly blue. I mean, positive. It's blue and positive. Huh? Sad? Blue. Well, the top region. Yeah, it's positively blue. Alright, so since I have electrons at the bottom of the cloud, what do the electrons in the ground want to do? Oh, they want to go away, right? Okay, so the electrons, they want to flee away from this negative region that's on the ground. Okay, so what I end up with, guys, is kind of a region of positive charge below the cloud and a region of negative charge on the sides of the cloud. Well, anytime I have a very strong positive charge and a very strong negative charge, we saw the other day with the Van de Graaff generator, what typically happens? Zap, right? Okay, I mean, y'all see this is kind of a battery? I mean, positive terminal, negative terminal. Okay, so what we see is those will, connect with a lightning strike. Okay, when that happens, charge is dissipated. Okay, so when that charge dissipates, the amount of charge in the cloud connects with the amount of charge in the ground. So in other words, there's less charge. There's less charge separation then. So at that point, the lightning strike stops. Okay, so it's a real quick burst of charge. Then that charge separation's gone as the lightning strike stops. Okay.
Is the zap or the visual of the lightning, is that us seeing electrons traveling through air?
What you're seeing is anytime excuse me. Air is an insulator. Anytime electrons travel through an insulator, the insulator gets really hot. So since the electrons are traveling through that insulator, the air gets really hot, and hot air, if it gets hot enough, will glow. Okay, fire. So that's one example. Or or if the particles get excited, then it will glow. So what you're seeing is those air particles getting extremely hot. In fact, during a lightning strike, the column which the electrons are traveling through can get hotter than the surface of the sun very momentarily. So you see that zap, particles get really hot. When the particles get really hot, what do the air particles do? They expand, right? So they expand really rapidly, okay? And then after they get cool, they come back, and so that creates a compression and a rarefaction, which is a sound wave, okay? So that's you're hearing the lightning as under there.
What if you get struck on?
Well,
Not
Looks like-
necessarily.
yeah, not necessarily.
You get struck by lightning,
One more example of conduction, guys. I want to demonstrate real quick how this little contraption works. Y'all know the very basis of that. It's called an electroscope. I have this little orb at the top, and that connects to this little stick, and then I have the two little floppy aluminum pieces down there. Okay. So let's say I take my balloon, has a whole bunch of negative charge up here, and this is neutrally charged. Okay, so all the electrons up here want to do what? Flee away. Okay, so that means all the electrons gather at the bottom, which leaves positive charge at the top. Okay, well, since this has negative charge and this has negative charge, what do they want to do? Repel. Okay, so they separate. So that indicates the presence of charge. When those two things separate, I know that induction is occurring.
What's in between the positive and the that little tube? What is
It's just like a little, it just connects them.
that?
Metal. Okay, so it just, electrons, if I put some electrons up here, then electrons go, they separate and they come down here to these two little foil pieces, and those foil pieces separate. Or the opposite could happen, right? If I put positive charge up here, then all the electrons would, protons, and they'd come up here, right? Okay, and this would become negatively charged, and this would become positively charged, and then go, they'd separate. Okay, so it could detect positive or negative charge. All right, guys, real quick, grab a partner, and wait for me to skip some slides, because I decided what I'm talking about. All right, and talk it out. Did y'all want to see the animation?
Yes.
Okay. All right. Okay. So we have the negative cloud there, and so that induces positive charge on the ground. And when the separation gets large enough, then we have a lightning strike that dissipates the charge. Okay. So talk it out.
Lightning is induction, so this separates the electricity within the actual object. No, for real. That's just the example. Yeah, that's an individual right, and the spirit is in the spirit. The light is close to it, and then the so they separate the protons. So same things repel each other.
All right, guys, let's talk. Number one, which direction does charge flow in a lightning strike?
Opposite charge. To the direction of opposite charge.
Okay, discharge flow. If I'm talking about discharge, I mean the charged particle. Which charged particle moves?
Opposite to negative.
An electron, right? The electron moves, and we said that there's negative charge in the bottom of the cloud. So it typically moves down. Okay, so that's actually a misconception about a misconception. Okay, a lot of people say, oh, there's a misconception about lightning. We said that lightning, everybody says that lightning moves down, but it actually moves up. And if I'm talking about the motion of particles, then that's not true. Okay, electrons physically move down most of the time, and there can be the opposite case, but most of the time electrons physically move down. However, in physics, sometimes we like to do dumb things, and one of the examples of dumb things that we've done is we define current as the direction of positive charge. Okay, so current in a battery would flow from the positive terminal to the negative terminal, even though electrons are going the other way. Okay, so current does flow from the ground up, but particles go from the cloud down. Okay, so that's where that misconception came from. They would say, oh, well, lightning goes up. Well, current goes up, but the particles are actually, the electrons are moving downward. And if you don't believe me there, then I have a little video. Okay, the part you're seeing right now is called the step leader. The step leader is where it's determining what path it wants to follow, and as soon as that connects with the ground, bam! Okay, that's called the return stroke. Okay, the return stroke is what y'all typically see, and there could be multiple return strokes. So that was that first one. It kind of fades. You know, sometimes you see it flash twice. Okay, that's multiple return strokes. You see it's fading here, and then kind of brightens back up again. Okay, that's the second return stroke. Okay, every time a return stroke is a delivery of charge to the ground. And we'll spend some more time talking about lightning, but y'all can see it indeed does travel typically from the. So you're saying in that rare other case? I don't know. Sorry. I can try to find a picture. Amazing upward lightning. That's probably fake, but we can look at it.
Has a million views in his feature.
Storm knows how to use YouTube, so.
That's always.
That's right. Like they're starting out with it.
You know, as a teacher, when they show stuff like when you click on something on YouTube, you think, "Dear God, please do not let there be anything." Yeah, that's fake. Yeah. This guy does have a good voice, so it could be real.
It sounds educational.
Yeah, typically if they have a good voice, I believe it.
Bring it free, you can say anything.
Yeah.
You're going to live.
How do you know
It could
you've
be
never
real.
seen it? To know that's true or not?
They just turned his
And
head upside down.
he's bald, so he must be smart. So I guess it's true. It's
Nothing going on with TV.
no, like I said, it's possible. So that could be that could be it.
Look at the comments and see
I have a PhD in physics, and this is not real. Somebody said gold in Spanish.
It's my friend.
This is in video recording. Let's finish talking with this, and then we can look at that. All right, guys. Let's finish talking about these, and then we'll waste time with that. How does an object gain positive charge through induction? By the electrons fleeing. Okay, so the electrons flee away, it gains positive charge. It doesn't gain protons. Okay, it loses electrons. Do you think inductors work very well for do you think induction works very well for insulators? Not really. Okay, in order for the induction to happen, charge has to be able to move, and charge doesn't move very well in an insulator. Okay, so water you can't really induce a charge in water. I mean, with a strong enough electric field, you can induce a charge in anything. But typically with water, we're not really going to see induction occurring. Okay.